Alright, so we will start now as soon as I'm zooming. So we are starting from page 1 from in your notes packet. Alright, so as you see, it says unit 9, exponential and log notes, and we're going to start with the graphing of exponential and log. So let's just look at the parent function. So it talks about a and b and so on and so forth. I'm not a big fan of these variables, so I'm just going to write this down for now. Just go ahead and write it down, and then I'll explain it. Like a lot of these things I feel with variables, it's kind of hard to explain, and then I'll talk about what exactly is an exponential function. Okay, again, there is exponential growth and exponential decay, and let's just take down again some things about variables. And again, once you understand it, once I explain it with numbers, when you want to go back and study it, it'll help to look at the variables too. Yes?
What is b greater than?
Oh, sorry, b is greater than 1, sorry. The base, which is the base, yeah. And I'll talk about this. B basically stands for the base. And here the base is between 0 and 1. Alright, so first we'll talk, yeah, I'll give you guys 30 more. Okay, so we'll start by talking about exponential growth. Okay, so growth generally means, whenever you talk about exponential growth, it generally means you're starting off with numbers close to 0. It could be 1, it could be 5, it could be something really close to 0 and grows into a large number exponentially very quickly. So it grows very quickly into a very large number, and that's what we're going to look at this. So how does something become an exponential growth? How does something become an exponential decay? So let's focus on the growth. So in general, the function of an exponential growth will look like this. So function is always f of x equals to, for now let's not have an a right here that they talk about an a, it's confusing. Let's just talk about, so when I talk about my parent quadratic, I say f of x equals to x squared, something really basic. I don't talk about an a, I don't talk about anything else. So for me to talk about a basic exponential growth, what makes it exponential is there is going to be a base. So let's take the simplest base, 2. Okay, so that's a constant. So let's compare this here. When I'm talking about a quadratic, x is my variable. X is my variable, but the square, it's every function is squared. My base is squared, but that's not going to be the case. This base could vary. The base could be 2, 3, and so on and so forth. Where the variable is it's in the exponent. So whenever you see a variable in the exponent, that becomes an exponential function. So that's what you need to remember. Whenever you see the variable in the exponent, this becomes an exponential function. What does this mean? This means that every time you go to the next point, you are multiplying it by 2. So 2 becomes 4, and you're basically squaring it. So you're not just multiplying it here, you're multiplying it here, and 4 becomes 8, 8 becomes 16, 16, no, I'm sorry, 8 becomes, no, I'm really wrong. Becomes 16, 16 becomes 16 squared, and so on and so forth. So you're basically squaring the numbers, 256 and so on and so forth. So you're squaring the numbers. So that's why it grows so quickly, because you're basically taking the numbers like that. Okay, so now let's look at what the values will be here. So if you're talking about, so you have a base. I don't know if you guys when the whole virus was going on, they were talking about how quickly is it spreading? How quickly is it spreading? Every person, are they spreading it 2 times, 3 times, 4 times, 5 times? So this 2 basically, this is the number that affects how quickly it's spreading. So we're talking about 2, that means every person is affecting 2 people. If they're talking about the current variant, which is what Omicron, something, subvariant of Omicron, they're saying it's 4 or 5. Whereas initially it was only 1.5 to 2, so you're seeing how quickly. So this is based on basically this number that we're talking about, the base, that actually talks about how quickly it's varying. Okay, so let's see how this looks like. So like any other graph that we try, any other function that we try to graph, we'll take 3 x values. Let's take -1, 0, 1. And y is nothing but 2 to the power of x. Y is nothing but 2 to the power of x. So here we're talking about 2 to the power of negative 1, which is half. Okay, so I just want to make sure that we remember how to do our exponent with, yeah, I just want to make sure we remember how to do exponent with a negative exponent. You guys remember that property? Anything to the power of negative, you flip it. So basically, if I have something like this, I'm going to take 2 to the power of negative 1 is the same as, what do you do? This is nothing, 2 can also be written as 2 over 1 to the power of negative 1. For you to write it as a positive exponent, all you do is to flip this, so this becomes 1 over 2 to the power of positive 1. That's why 2 to the power of negative 1 is basically half to the power. So same thing, I can take it in any way. 2 to the power of 2 over 3 to the power of negative 1. This one is easy. It's 3 to the power of 2 to the power of positive 1, which is just 3 to the power of 2. So you always take the reciprocal of this one. So 2 to the power of negative 1 is half. 2 to the power of 0. Anything to the power of 0, you guys remember? 1. Perfect. Awesome. Anything to the power of 0 is going to be 1. And 2 to the power of 1 is 2. So what you notice here is that any number you take, even if you take a negative number, negative 2, even if I take like say negative 3, 2 to the power of negative 3 is going to be 1 to the power of 2 to the power of q. I'm just giving you an example, which is what? 1, 8. It is still positive. So even if I keep taking negative numbers, I will get a positive value, though that positive value is going to get smaller and smaller and smaller. If I take negative 10, 2 to the power of negative 10 is going to be 1 over 2 to the power of positive 10, which is 1 over 2 to the power of 20, which is a really small number. So it gets smaller and smaller. So what is it getting close to? It gets smaller and smaller and smaller and gets close to 0. That's basically what it is. So okay, first of all, let's plot this. When x equals to negative 1, it's half, y equals to half. When x equals to 0, y equals to 1. And when x equals to 1, we're talking about 2. Okay, as x is getting, like I showed you, as I take values, many negative values, negative 3, negative 10, what's happening here, it is still in the positive y-axis. My y is still positive, 1/8, 1/20th, but it is getting closer and closer to 0. So basically this will grow really fast. On this side, it will never cross the y-axis to the negative side. It will just get closer and closer to 0. That means I have a horizontal asymptote of y equals to 0. This is good. So all exponential functions have a horizontal asymptote of y equals to 0. So that is my basic exponential function with a base of 2. Depending on the base, the graph will grow faster, but it's always going to look like this. It's going to have a horizontal asymptote. So all exponential functions have horizontal asymptote. All logarithmic functions have vertical asymptote. One of the easy ways to remember is, I always tell my student, exponential comes before log, horizontal h comes before v. So an easy way to remember, exponential is horizontal asymptote and log is vertical asymptote. So just in case you get confused which is what. Okay, so let's go ahead and write down some of these pieces of information. So the asymptote is always at y equals to 0. Okay, so the y-intercept, this is one graph where the origin, do you see there's no origin at 0, 0? Everything, cubic, quadratic, cubic, square root, all of them have an origin at 0, 0. They all go through 0, 0. And from there you do the transformation. This one, the origin is actually at the y-intercept, 0, 1. And the reason is, I'll tell you why. The reason is because of this. Because of this. Anything to the power of 0 is always going to be 1. So 0, 1 is going to be standard in every parent graph. 3 to the power of 0 will still be 1. 4 to the power of 0 will still be 1. So this y, there will always be a y-intercept of 0, 1. From here it could move. If your graph, we'll look at the transformation, but the transformation could move up or down. But this is always for the parent function. Domain, can we all read the domain? What do you think the domain is? We all know how to read domain. What do you guys think the domain is? Negative infinity to positive, because on this side it goes on forever, right? And it also goes on forever on this side too, because it's growing. So there will be x will be equal to 10, it will be equal to 1000, it will be equal to, so it's negative infinity to positive infinity. And what about the range? Can we all run our pen or pencil on the y-axis? Where does it start at? What's my lowest y value? 0, right? Except 0 is not included. So it is 0 technically, but 0 is not included, so you will put a parentheses and not a square bracket. And because it starts right after 0, 0.0001 is also inclusive. Except 0 alone is not included, but it starts right at 0 and it goes forever. So that's your range. Everybody good? Okay, so that's your basic exponential growth. That's your basic exponential growth. Okay, let's look at decay. When does a function become a decay? It becomes a decay. So this is the difference, where the base for exponential growth, the base is greater than 1, and exponential decay, the base is less than 1, but it has to be greater than 0. We don't have a negative number as a base. So it is still greater than 0, but it's less than 1. That means it's a fraction. So if I look at this is my exponential decay. Why? Because my base is half. So you're basically reducing the value by half every time. So let's go ahead and again take some values, 3 values, -1, 0, 1, and see what happens. And y equals half to the power of x. So one more time, it is an exponential decay when the base is less. Okay, let's write this down. When the base is less than 1, it's basically a fraction, but it cannot be negative. That's the key thing. And it's an exponential growth when the base is greater than 1. That's the key thing. That's what differentiates a decay and a growth. So when the base is half, let's see what's happening here. So can we all fill in the y? Without my help, can we all fill in the y value? So we're looking at half to the power of -1. What is half to the power of -1? What is half to the power of 0? What is half to the power of 1? Go ahead and write those values down. We all know properties of exponents. So half to the power of -1 is what? So you flip the half to make it +1. Does everybody agree with me? It's 2. Because you take half and flip it, it becomes 2. Anything to the power of 0 is 1. So that's why my key point is 0, 1. This is almost your coordinate origin, 0, 1. So that's why I said that there's always a y-intercept of 0, 1. That's always going to exist. And then the last one is half. So you see how it's starting from 2 and becoming half really quickly. So it's a default asymptote. So the asymptote is always horizontal at y equals to 0. And at some point I'll write down the note that exponential graphs have horizontal asymptote and logarithmic graphs will have vertical asymptote. Y-intercept always, okay, we didn't graph it. So at -1 it is 2. At 0 it is 1, and at 1 it is half. So what do you notice here? If I just connect these 3 points, and remember we learned this in interaction functions, you always go towards the asymptote if there is an asymptote. So on this side there is an asymptote, so it will go towards the asymptote. There is no vertical asymptote, so there's nothing to go, but the values will slowly increase. So it's like the x value will be really large and it will slowly come down to almost 0, and that will be our goal. We want your virus to follow exponential decay because you want many to be killed to almost 0. So that's how you so look at the difference between the graphs. Starts off at 0, grows really quickly, really fast. Starts off with a really large number, becomes small really quickly. Okay, the y-intercept, again same thing. This is my y-intercept, 0, 1. That doesn't change for the parent. Doesn't matter what the base is, domain is the same, it goes on forever in both direction. And the range is also the same. It starts at 0, not including 0, and goes up to infinity. So obviously these exponential, therefore log, and I'll tell you why we study log, I'll get to that. But exponential functions are obviously very important in a lot of different areas, especially scientific applications, because the whole idea of studying viruses and stuff like that is scientific, talking about labs and stuff like that. So that's why it's really useful. All right. Now that we've studied the basic exponential graphs for a base of 2.5, let's quickly look at some of the transformations. We're only looking at the transformation. We are not graphing it. So transformations always follow the same rule. Doesn't matter whether you're talking about quadratic, cubic, or whatever, including for exponential graphs. So this is your A. So that is basically your vertical stretch or compression. And then this is this. Do you guys know what, when a number is attached to 3, what is that? Okay, let's quickly look at a quadratic, that because that's our base. So y equals to, I don't know, half x minus 3 square plus 5. What are the different transformations taking place? Half is my vertical stretch or compression. In this case, it's a compression. What is this 3? It's a horizontal shift, right? It's a horizontal shift of, and it goes in the opposite direction. So it's negative 3, so it'll move 3 units forward. And what is this 5? It's a vertical shift, right? 5 up. You guys remember this? So my parabola will start at positive 3, 1, 2, 3, and up 5 somewhere here. So my parabola, and it's positive, and it'll grow slowly, slower than the normal. So it'll look like something like this, a broader and so on, so right? That's how I basically do my transformation. Exactly the same thing. This is your vertical compression, so it'll grow a little more slowly. And what is this 3? Okay, so that's why I came to you guys. So I'll write here 1/4 compression, vertical compression. Okay, let's just write this down. But what is that 3? Who can tell me what that 3 is? Any number that's attached to x is horizontal, right? It's going to be horizontal. Because remember, my parent was y equals to x square. So any number attached to x is your horizontal shift. So that's 4. This is also going to be a horizontal. What is it? X plus 3. So it's going to be 3 units backwards. Because it's plus 3, so it'll go left. Does that make sense?
Even though it's not in parentheses.
I'm sorry?
Even though it's not in parentheses, it'll still go.
Yeah, because it's still a part of the x. Because okay, I'll look at this. This is the one that's the part of y, because it's outside. So because it's part of the exponent, anything in the exponent is part of x. Correct. Yeah, that's a good question. So her question was, it's not in parentheses, and she's absolutely right. But the fact that it's in an exponent, and maybe that's why it was confusing. Maybe because it's in the exponent, it is part of x, and the vertical shift is basically this one, -4. Okay, so let's go ahead and write down. This one only has a horizontal and the vertical shift. Let's write down both. What's that, -3? I can't read. Yeah, -3. So it's going to be 3 units forward and 4 units down. So this is the horizontal shift. And this is the vertical shift. All right, we're doing okay? All right, I'll wait for 30 more seconds and then we'll go to the next page.